Hello everyone, welcome to another session in the deep learning series. Today we'll continue with discussing the fundamentals of neural networks. Right? In the previous session, you would have got an idea of basically what are the input layers, what are the hidden layers, at least sort of a basic introduction to terminologies. Right? So we'll continue with that. So in this particular, again going back to the same image of a neural network, right? So all these connections which you see over here, right? Connection, maybe it could be connection from I1 to J1 or connection from J1 to K1. In general, all of these connections are nothing but your weights between these two nodes. Okay. So, in order to sort of clearly understand this, so let us sort of take a step back and we look at sort of what we've discussed previously. So if you remember in the previous sessions, I think at least in session of linear regressions, right? Basically, what is the idea, the whole idea of a linear regression is, you have a particular set of inputs. You're basically trying to define a function, right, which should basically map your input to your output. Okay, consider a case when you're basically trying to predict sales of a particular product, right? So basically what you're trying to do is, given a set of input data, it could be maybe historical sales of a particular product or along with other associated information. Basically what you're trying to do is you're basically trying to figure out, or you're basically trying to develop a function which would basically map input to your output, right? That is what fundamentally what is happening. You obviously definitely you have your linear regression equation. Say if it is w0 plus w1 x1 plus w2 x2, over there you're basically trying to find the optimal values of weights. Over there weights are w0, w1, w2 and so on, right? So for that input data, you're basically trying to find the optimal values of w0, w1, w2, which would map which would basically map to the output and sort of gives the lowest error, right? You're basically minimizing the error over there, right? So that is what happens in linear regression. In a very, very similar manner, over here also I think it's actually very similar, right? Over here also you have your inputs, you have your set of inputs, and you have your set of weights, and you have your output. So basically what this particular part, right, this particular part is this is that function which you are basically trying to define, okay, which you're basically trying to learn from your data, right? So basically all of these weights are the ones which you learn from your data, right? In your linear regression you had your w0, w1, w2 and so on, right? So those are the things which was learned from the data, right, where you basically minimized an objective function, you basically defined your cost function, you defined you define maybe in certain cases regularization, and overall you're minimizing. With that you're basically trying to find the minimum value of w0, w1 and so on, right? So that was what was happening in linear regression. Over here also fundamentally the idea does not change. You're basically trying to define a function which should map your inputs and your outputs. That is what the whole idea, overall idea is, right? So these are nothing but, I think the correct technical term would be universal function approximators. So for any type of input data, right? So it could be text, it could be image, or it could be even normal structured data, right? So you would sort of just calculate the optimal values of your weights. It could be w1, wi1, j1, wi2, j2 and so on, such that you basically get the optimal values of those weights under the condition that you're under minimum error, right? So that is what is at a very high level what is neural network is, right? In order to do that, right, so there are different sort of building blocks. So today I think we'll look at the first building block. So the first building block is basically something which is called as an activation function. Okay, so what basically is an activation function is, activation functions are so before I actually explain what is an activation function, right? So let me sort of actually walk you through what actually calculations in the neural network. Okay, So consider this particular case, right? So this is again the same neural networks which I think which was actually seen in the previous image, right? So you have your input layer, you have your hidden layer H1, hidden layer H2, and you have your output layer, right? So these are the inputs. Okay, these are say 0.1, 0.2, 0.1 inputs. Now basically what happens in a neural network is, suppose you have your values I1, I2, I3. These are the values. So this is your weight. This thing is your weight matrix, right? Weight matrix for this particular, these two. Say weight matrix for your input layer and your hidden layer H1, right? So this is I1, J1, and so this is I1, J1, I2, J2, I3, J3. That's your first row. Second row is I2, J1, I2, J2, and this is second row. This is your third row. So basically what happens, at least in the initial step, is you basically do a basic cross product, and you just add the bias to it, right? So you have your inputs, multiply with the weights. So weights, usually what would happen is weights are usually initialized. So again, there are whole set of whole lot of theory behind determining what would be the optimal values of weights which are initialized, but at least for sort of the sake of simplicity, I think we'll just consider that it will be initialized with some random values. Okay, so basically what would happen in the first layer is you basically have your I1, I2, I3, I1, I2, I3. So you just basically take a cross product, add the biases at the end, okay, and you basically get your HIN1, HIN2, HIN3. Okay, so these are these. Now after this, so this is now what is this H1 out 1, H1 out is nothing but, so this is where your concept of activation function comes. So there are different types of activation functions. So basically you can think of it as some sort of function, right? So whatever input values you get, so whatever values you get after your multiplication of your cross product and adding the bias, whatever values you get, you basically pass it through this particular activation function. Whatever the output you get, so that is nothing but your output to that particular layer. Okay, so why are activation functions needed? Because mainly, you see, all of these are nothing but your normal linear operations. Okay, so without any presence of any activation functions, it would just be a normal linear regression, right? Which we don't want, right? So the whole idea of basically using a neural network, or maybe even working on deep learning systems, is to basically develop more complex models, more complex systems which are capable of learning more and more patterns in your data, right? If I say, suppose you have a linear regression which has an accuracy of 50% or 60%, your whole idea of actually developing such a complex system or such a complex model is it would basically learn better patterns, so it would be a better model. The model will perform better than, say, a linear regression, right? So that is what the whole idea or overall idea of working on these neural networks. Okay, now suppose if you don't have any of these non-linearities, right? So the whole idea of activation functions is activation functions basically introduce non-linearities to your model, non-linearities to neural network. Okay, so this particular case is basically, this is one particular type of activation function. This is basically an example of ReLU. Okay, so there are different types of activation functions which we will learn in the next few sessions, but this is what basically happens. So you basically have your input from your, say, cross product and addition of bias, that you basically pass it through your activation functions to basically end up with the final value. Okay, so this is what is activation functions. So there are two types of activation functions. One is linear activation function and the other one is non-linear activation functions. So we'll actually go through that in detail in the next session. But before that, I think there's one main sort of neural network idea which I sort of did not explain until now. So what basically that is, how basically neural network works, right? So you, as you would, again, taking the example of a simple linear regression. What would happen in a simple linear regression is you basically have your input data, right? You have your weight values which needs to be calculated for that particular input data, and suppose you run gradient descent to find the optimal values of weights, right? You basically run a gradient descent to minimize the objective function and get the minimum values of weights. right? And whatever weight values we get, you put it in your linear regression equation, and that would be it, right? So that would be your simple linear regression model. Okay, now basically what would happen, so again coming to neural networks, now what would happen is, suppose these are your inputs and this is your first pass. So okay, again consider the same linear regression concept, right? You calculate your values of weights, right? You would basically run this calculations, right? You would basically use I1 I2 multiplied by this, then addition of bias, right? You would basically do all of this. So you move from input to hidden layer, input to H1, input to layer H1, you would basically get your H, you would basically get your output. Again, in a similar manner, you would move from hidden layer H1 to hidden layer H2, you would basically get your output, right? And finally, you will end up with some value at the output layer, correct? Now this is, again, everything is sort of similar. You might think that everything is similar to sort of linear regression, right? But there's actually one sort of twist over here. The sort of twist over here is there's something which is called as back propagation. Okay, so back propagation, basically what happens is, after you get a particular value over here, right, after you basically get output over here, so you again go back, you again calculate the gradient, right? So back propagation is nothing but, I think in a very simplistic term, it's nothing but you're basically calculating the derivative of your error with respect to your weights, okay, and you're again sort of going back the same route. You're going from output to H2, again you're going from H2 to H1, H1 to input. Okay, so that is basically what is a complete this thing of complete cycle of a neural network. So you have your forward pass. Forward pass is what we just saw, right? You take a cross product of your inputs, add your bias, then pass it through activation function. So you'd be doing that for all layers, input to H1, H1 to H2, right? Now this is your forward pass. Backward pass is your back propagation. You'll be moving from output to H2, and you'll move from H2 to H1, H1 to input, and so on, right? So that is your back propagation. So combination of your forward pass and backward pass is what completes your one cycle of neural network. Okay. So one of the main reasons why it was not explained in the beginning was I want to make sure you actually understand this particular concept. What sort of calculations happen in a neural network, right? So over here, right, over in this particular example, whatever you saw, max of 0 H1, max of 0 in H2, right? So these are nothing but your ReLU activation function. So instead of ReLU, you could have sigmoid. Again, that would nothing but be but another one more set of formula, right? Over here, instead of max, you would have again a particular set of formula. Whatever input you get from this particular operation, right? This particular operation of I1, I2, I3, Wi1, J1, I2, J2, I3, J3. So this particular operation, whatever is the output. So this output will basically run through your sigmoid function, right? So that output, that will be only the forward pass. Then again, you have your backward pass or back propagation, wherein you're basically calculating derivative with respect to your weights. Okay, for each layer. Again, when I say each layer, you basically mean output to H2, H2 to H1, H1 to input, and so on, right? So we will discuss in detail. We'll actually in the next few sessions, we will basically take up an example where we'll run through the forward pass for each layer. Again, we'll calculate backward pass values for each this layer as well. That also I think we will be discussing in the next few sessions. But yeah, before that, this is basically what has happened. This is basically what happens in neural network: forward pass and backward pass. I think in the next session we'll basically discuss different types of activation functions and what are the advantages or the disadvantages of each of them. Thank you.